This is the second part of the pre-lab where I'm going to talk a little bit more about the specifics of your procedure for this particular lab. There are generally a lot of questions on this lab, so I'm hoping that this will answer those questions before you come in so that on the day of the lab you actually know what you're doing. Now, the specifics of the job plot that you will be creating. First up, I'm telling you right now, the sodium hydroxide and the unknown acid, both of the unknown acids, I am telling you they are all 0.1 molar solutions. This is going to be critical for us because the whole point of the job plot is finding the correct mole ratio. If you don't know the formula of a compound, you have to know something about its concentration. You have to have a way of controlling something about its concentration so that you know you're getting the actual mole ratios when you're doing your analysis. Because molarity is moles divided by liters, if we know that both of the solutions have a 0.1 molar concentration, that means that we're making the molarity equal. Additionally, because we are controlling the volume, because we're not putting in random volumes in there, and that we're making sure that we're always being very, very careful about the milliliters being used, we're also controlling the liters. So this is being controlled. The liters are being controlled, which is why right here we can make this statement that the volume ratios being used, because the molarities are the same, the volume ratios being used are actually being used as a stand-in for the mole ratios. So when we look at, just to read the second bullet point right here, if your two solutions have the same volume, they must also have the same number of moles, right? If you have 25 milliliters of 0.1 molar NaOH and 25 milliliters of 0.1 molar unknown acid. Unknown acids are always abbreviated as HA. H for the hydrogen that's in all acids, A for the anion, or for acid for all the other stuff right there. If you plug in 25 milliliters and 0.1 molar into the molarity formula for both the NaOH and the HA, you're going to find you have the same number of moles. And the reason you have the same number of moles is because you have the same volume. 25 mils to 25 mils will be the same thing as the number of moles will be equal. Same thing as the number of moles being equal. So this is critical for us. Understanding that because we're keeping the concentration of both of these solutions identical to one another, because of that, because we know it's 0.1 molar base and we know it's 0.1 molar acid, we can assume that the volume ratios are the same thing as the mole ratios. This will allow us to extrapolate the correct mole ratios. Now, the volume ratios that you're going to be looking at today, you have to keep the total volume always of your reaction, total volume always 50 milliliters. And you're going to be doing 45 to 5, 40 to 10, 35 to 15, etc., 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 all the way up through 5 to 45. So you want to carry this all the way through. So this is, if you're saying, I think it starts with base to acid, but I am honestly not sure which one it says to do first. So this would still be base to acid, but you flipped it around, right? This is a 9 to 1, whereas this is a 1 to 9. You're going to carry through all these ratios all the way up from 45 to 5 to 5 to 45. Total volume always has to be 50, and remember that this ratio right here, the 9 to 1, the 1 to 9, in the case of the 40 to 10, the 4 to 1, that's representative of the coefficients. You're basically asking, is the correct coefficient between the base and the acid? No, is the base 9 and the acid 1? If you get the most product on that particular trial, then yes, that it would be considered the correct ratio, the correct coefficients. Our job plot, a note on the initial temperatures. because you're going to start by taking the temperature of the sodium hydroxide solution and the unknown acid solution separately from one another. If they are not the same as one another, if they do not have the same initial temperature, you have to make a correction for that, because we're calculating change in temperature. You are actually not plotting the final temperature reached, but the change in temperature. And so if you've got two things that are starting at two different temperatures, you have to account for that. And the way you're going to do that is by taking a weighted average of the two initial temperatures so that you get one initial temperature overall. The lab handout has the instructions on how to do that. It's a very straightforward weighted average where you're taking into account, how much of your reaction is the sodium hydroxide, how much of it is the acid, and weighting it towards whichever thing there is more of. Now, the job plot that we're going to be making is going to have axes that look like this. I do want you to put the sodium hydroxide on your x-axis, that particular reactant, because you know a lot more about the sodium hydroxide. You know its formula. That's the big thing that you don't know about the acid. And then we're going to put change in temperature in degrees Celsius on the y-axis. And then just to kind of go through and show you what your graph might look like. Again, you're going to have data points for all of these. Is not the 50, but for all of these points. So right here, when this was 5 milliliters of NaOH, this is representative of the trial where you also had 45 milliliters of the unknown acid. And you're going to plot your change in temperature on the y-axis. So this would be trial 1. So you're going to be doing a whole bunch of different trials here and then plotting each of them individually. Trial 1, maybe your change in temperature was, I don't know, here. So you're going to plot the points. Each of them is a trial. So this would be trial 1. This would be where you had 10 milliliters of NaOH to 40 milliliters of unknown acid, HA. So that's trial 2. And maybe your graph looks a little bit like this. I think I hit every point there. Your graph's going to look like that. You're then going to want to draw straight lines for the straight line segments. So in Excel, you can create a line that goes there, and then a line that goes down like that. Maybe, I am not saying that this is what your job plot will look like. I'm saying that there's a possibility that this is what your job plot will look like. From this particular graph, it's fairly clear that this is when we're getting the most product, because product in this case is change in temperature. Again, this is an exothermic reaction, so we're measuring how much heat is being released. And then you just go down and you say, okay, what does this correspond with? What does this correspond with? This seems to correspond with having 25 milliliters of NaOH and 25 milliliters of the unknown acid. Well, the ratio 25 to 25, if we turn that into a coefficient ratio, that's a 1-to-1. And it's saying that we got the most product when we had a 1-to-1 mole ratio. That's one possibility. There are several others. Again, I am not saying that that is what is going to happen. I am saying that it could happen, and it's an example of interpreting the data. It might also happen that your job plot could look something maybe like this. Have a line that goes up, and then maybe a line that looks like about there. And again, you want to extrapolate and find when are we making the most products. In this case, it looks like it's about 30 milliliters of NaOH to 20 milliliters of acid. This would turn into a 3-to-2 coefficient ratio. Because this is saying that we've produced, in this case, we seem to produce the most product when we had 30 milliliters of sodium hydroxide and 20 milliliters of the weak acid. Again, going up and going down, there is a limiting reactant. There is no limiting reactant when we're making the most possible product, because that's when we have the perfect ratio, the quote-unquote perfect ratio. When everything has been idealized and everything is reacting. Theoretically, there shouldn't be any excess reagent at the point where we're making the most product. Everything has been used up. So those are the specifics. I have a feeling that we're going to need to share data about unknown 1 and unknown 2, but I'll tell you that on the day of the lab. I'll have half the class, I'll assign half the class to unknown 1 and the other half of the class to unknown 2. And you'll all have the sodium hydroxide. Every group is going to be responsible for creating 2 job plots, but you might just be doing the lab procedure for one of the unknown acids. But you're going to do a job plot for each of the unknown acids, but it might be with someone else's information. Make sure you include in your lab report what group's data you were using. You don't want to simply say, you don't want to steal data if you didn't, you don't want to have people assume that you did all the work yourself if you actually didn't. So I hope this helps. If you have any additional questions about this lab before we begin, please, please, please come in to see me.